Hi, I'm Alex.
I'm Amy.
I'm Cecile.
I'm Sam.
We are second year physics students studying at the University of Durham.
Our target audience is university level non-physics students.
And the question we have for you today is:
do your actions in the future affect your present?
How would you feel if what you chose to do tomorrow affected what you did today? How does the quantum world affect your free will? Does the universe only exist when we are observing it? Quantum mechanics is the study of the very small. More explicitly, it focuses on how particles at the fundamental level are not as solid as we might think them to be. Electrons are part of the fundamental matter we are made up of, and yet they act like both particles and waves at the same time. Yet are neither of these. These waves/particles can be described using the state vector. This essentially describes all the parts of the individual that you could want: momentum, position, and energy at a specific time, and some more complicated quantities such as spin. Parts of this state vector can be used to make a wave function, which, when multiplied by its complex conjugate, a kind of way of squaring the wave function, we get out the probability. That's right, probability. In the quantum world, things are uncertain. No one object has a defined state. This idea of the incredibly tiny being probabilistic instead of deterministic is a fundamental concept that underlies all of quantum mechanics.
My name is Tom Lancaster. I'm Professor of Physics at Durham University. My interests are quantum and classical field theories and magnetism in condensed matter.
How do you briefly explain quantum mechanics to someone of a non-physics background?
So how does one usually go about this? I think one would usually talk about wave-particle duality. I mean, that's the standard way in. That's the way Feynman does it. And then you would probably go on to tell people about scattering. And then the choice is yours. You can, depending on your background, you would probably go down the route of pure and mixed states, or you would potentially tell people about relativity in many particles. Okay, so those are the sort of ways in that people have classically used.
The mathematical theory of quantum mechanics is one of the most successful physicists have ever created and has extraordinary predictive power. What we mean by an interpretation of quantum mechanics is an attempt to explain how the mathematical formalism relates to reality. There are countless interpretations, ranging from ones which say parallel universes exist, to ones which suggest our universe comes from a system Darwinism. The most popular interpretation by far is known as the Copenhagen Interpretation. It acts as a solid foundation for a lot of the other interpretations. One of those interpretations, and the main focus of this video, is the Transactional Interpretation put forward by John G. Cramer in 1986. The Transactional Interpretation fixed a lot of the major interpretational problems with the Copenhagen Interpretation, while still providing the same links between the formalism, relating the maths to the real world.
When we refer to the complex conjugates, we are talking about taking a complex number and making the imaginary part of it negative. So sometimes we'll have a complex number that, for example, could be 3 plus 2i, and with the 2i being the imaginary part. To find the complex conjugate of 3 plus 2i, we would just make 2i negative. So we would end up with 3 minus 2i. A function describes the state of a thing. A thing can be anything. You and I both have a wave function, but we're a lot less wavy than something small like an electron.
Causality does what it says. It describes how stuff in the past comes before the future, and the present comes between those. It says that in a universe that is causal, things that happen in the future can only be affected by things that happen in the past. If a universe has the property of locality, that means that only things within your local region can affect you. To help you understand this, it might help to envision what are known as light cones. We'll take an axis where our horizontal represents where we are in space, and our vertical represents the passage of time. If we were to stay still in space, we would still go up in time no matter what. Now we can draw two light lines coming from you. These represent your movement if you're travelling at the speed of light or very close to it. Because the speed of light is the universal speed limit, nothing being able to go faster than it, everything outside these lines, outside the space and time, is forever out of your reach. You can never affect something at that position in both space and time. This is what we mean by locality. An object not local to you is one that you could not affect by travelling at the speed of light. Separated parts are only correlated if they retain the possibility for light speed contact. Locality is important as it prevents what Einstein referred to as spooky action at a distance. We will see that the Copenhagen interpretation tries its best to hold on to the threads of locality, but these are very quickly coming loose. The transactional interpretation, which looks at the Bell inequality tests, says that the quantum world must be non-local.
Realism is the idea that nature exists independently of man's mind. Experiments theorised by Bell proved that the universe is either non-local or it is not real, the latter of which means that the universe does not exist until observations are made. The Copenhagen interpretation, as mentioned previously, is the most popular interpretation of quantum mechanics, and has 5 fundamental underlying principles. The first 2 describe the formalism, the maths, and the latter 3 describe its interpretation.
The first, C1, is the Heisenberg uncertainty principle. Fundamentally, it states that 2 related, or more formally, canonically conjugate variables can only both be known simultaneously to an arbitrary degree of accuracy. If you know a lot about one variable, you don't know a lot about the other. C2 is the statistical interpretation of Born, which says that the probability distribution for a particular quantity is given by the amplitude of the wave function.
Then we have the interpretational principles. C3 states that the uncertainty principles from C1 and the weird wave-particle duality we mentioned at the start is not an aspect of the process of measuring a system, but rather an intrinsic property of nature. C4 says that the state vector is not a physical object, but is instead a representation of our knowledge of the system.
C5 narrows the focus of the Copenhagen interpretation, not on meaning or reality, but exclusively on observables.
Before we move on to the main problem with the Copenhagen interpretation and the overview of the transactional interpretation, we need to have a look at the Bell inequality tests. During the first advent of quantum mechanics, there raged a debate between 2 sides. One side argued that the physical world must be locally real, and said that particles that are very small have hidden variables, ones that we cannot see, that decide the properties of the particles, and that when we measure the properties of the particles, it's these that come to light. The other side said that no, this isn't true. There aren't any local hidden variables, and the universe can be non-local.
John Bell came up with the Bell test in 1964, which would rectify this argument, and as of 2015, all of the Bell tests have found that theories which use local hidden variables are inconsistent, and that therefore the opposition is more favourable and the universe can be non-local. Whilst looking at the Copenhagen interpretation, we'll see that C4 provides the most issues. But first we need to understand why it was introduced. As mentioned in our definition of locality, it is often spooky to imagine a system being non-local. To prevent this, the Copenhagen interpretation demands that our models be local. C4 does not deal with the Bell inequality test, as the Copenhagen interpretation was argued for before they were formally tested, and so instead it chooses to almost sidestep the issue altogether. Within the Copenhagen interpretation, if we were to imagine a spherical wave propagating from a single point in space, almost like an expanding bubble, we would see that upon reaching the observer, the bubble would instantaneously pop everywhere and only be present at the location of the observer. This idea of the bubble popping instantaneously provides a real issue, as it implies that the process is non-local. Instantaneous action happens faster than the speed light travels. To get around this, C4 states that the bubble and its resultant popping is in fact not a physical process, but a representation of our knowledge of the system. However, another problem stems from this that is not obvious. When we declare that a quantum system, the state vector, is dependent on our knowledge of our system, we explicitly place a special focus on intelligent observers, which is not explicitly stated within the formalism which describes quantum theory. This overall essentially implies that the universe only comes into being when someone is there to watch it. When a tree falls down in the forest and no one is there to hear it, it wouldn't actually make a sound.
We'll have a look at the transactional interpretation, which was first proposed by John G. Cramer in 1986. It attempts to solve the problems of the Copenhagen interpretation. This model explains all quantum processes as a kind of handshake. It sets about 4 main goals for what it wants to do better than the Copenhagen interpretation. 1. Isolate the micro from the macro. An observer on the large scale should not have to affect the small for things to occur. 2. Account for the non-local correlation of the Bell inequality test, while also being consistent with relativity and causality. 3. We want to be able to account for the collapse of the wave function, the bubble popping, without the need for the subjective triggers. 4. Overall, we want to add more insight and meaning to the state vector, and provide insights to hard problems. Like the Copenhagen interpretation, it has 5 main premises.
The first premise of the transactional interpretation is exactly the same as the Copenhagen, the uncertainty principle, where 2 related variables cannot be known simultaneously. Likewise, the second premise is exactly the same as well. The transactional interpretation does not alter the statistical character of quantum mechanics, but gives us a glimpse of the dice at work. The third says that the uncertainty principle is just a manifestation of a given transaction going to completion. It can project out only one of a pair of related variables. The fourth says that the state vector is taken as a real physical wave that is identical to the offer wave in the transaction. We'll get on to what an offer wave is in a second. The fifth and final says that observables are firm predictions of quantum theory that can be experimentally tested. Inferred quantities are not verifiable and are for interpretational use only.
When we look at solutions for the electromagnetic wave equations, electromagnetism being the study of particles of charge and waves generated by charges, it's found that there are solutions that imply waves that travel both forward and backwards in time. Normally the backwards through time travelling waves are disregarded as they are unphysical. However, using this concept, we can develop the transactional interpretation.
We start with an emitter and an absorber. The emitter starts the transaction by emitting both a forward time wave, which we'll call F1, and a backward time wave, which we will call B1. We call the point at the time of the emission T1. Eventually, F1 reaches the absorber. This is known as the offer wave. The emitter is sending an offer to the absorber. At this point, the absorber recoils and sends back a confirmation wave. The absorber lets out a forward and backwards travelling wave of its own. We'll label these F2 and B2, and we'll call this moment in time T2. B2 then travels back to the emitter at the point of emitting F1 and B1. Remember, it's travelling backwards in time as well as through space, and so it can return to when the emitter started emitting. This is what we call the handshake. It is as though the emitter and absorber were shaking very wavy hands. However, you'll notice something. We're left with waves coming out after T2 and more worryingly before T1. So what happens to these waves? If we take a closer look at F2, at the moment the absorber recoils, it is produced in such a way that it cancels with F1, meaning that after T2 there is no wave, and if we look at the backwards wave, we find much the same thing as before T1. As we did after T2, the 2 backwards waves before T1 are cancelled out as well. This process of waves being exchanged happens several times over the course of an interaction, but it is important to realise that the transaction never takes longer than it takes for F1 to reach the absorber because of the nature of the backwards in time's waves. The transaction happens between time. To someone not privy to the goings-on of the backstage, they would see a normal quantum mechanical interaction, a regular transfer of energy, but if we could see the full thing, we would be able to see much more complex goings-on.
So how does this provide us with any insights? Let's have a look at the wave that now lies between T1 and T2. When trying to make a prediction within quantum mechanics, we use the Born statistical interpretation, which looks like this. So what does this equation mean? Born's rule gives us the probability distribution for our system. It can tell us what the probability is that our particle is at some position at some point in time. As we see, it depends on the wave function. The Copenhagen interpretation gives no explanation for Born's rule. However, using our handshake model, where we take the wave function to be a real wave, we can see that phi is the forward part of our wave between T1 and T2, and phi star is the backwards part of our wave. The transactional interpretation provides insight on something fundamental that the Copenhagen interpretation could not.
Everyone's heard of Schrödinger's cat. The thought experiment involves a cat inside a box containing a mechanism that has a 50% chance of poisoning and killing the cat after an hour. This works through the use of a radioactive source and a Geiger counter. You lock the cat in the box and return after an hour and open the box. What is the state of the cat just before you open the box? The Copenhagen interpretation would say that the cat was in a superposition of being both dead and alive. Only once you observe the cat does the state vector collapse to one of these states. This seems absurd. It may not be obvious at first, but what Schrödinger was really asking was, when does the state vector collapse? Is the cat at some point both 50% alive and 50% dead? The transactional interpretation's answer is that the transactional process is atemporal. The emitter and the radioactive source emits a very weak alpha wave such that it may or may not be confirmed by the absorber at a rate of around 50%. If the transaction forms, then the cat is killed, and if not, it survives. In this way, the cat is never 50% alive or 50% dead, and we are never waiting for the arrival of the observer. A follow-up question that the Copenhagen interpretation asks is, when can a quantum event ever be finished? Is it when the Geiger counter activates, when the poison is released, when the cat is killed, when the observer observes, and so on and so on? When using the transactional interpretation, we never run into these issues. The quantum event is simply finished when the transaction is finished, which, because it happens between times, means it is finished when the absorber absorbs the first wave.
Have you heard anything about the transactional interpretation?
Yeah, so that would seem to me to use the notion of a Feynman propagator, which within quantum field theory is the way that you can have things essentially propagating forwards and backwards in time, so a time retarded and a time advanced part, and basically adds them together, and you use that to encode fields in terms of the language of particles and antiparticles. And you can tell stories about antiparticles travelling backwards in time, but no one believes them anymore. That's just an interpretation. If you start to believe that realistically, you get something like a transactional interpretation. But I think ultimately it's killed off by the fact that one of the reasons why quantum field theory is so important and works so well is that the same theory that describes relativity is also the same theory that describes many particles. But the transactional approach, at least as far as I understand it, doesn't really provide a good explanation or a good description of many particle physics. It provides some sort of vague analogy. Okay, which is the opposite of what it was designed to do, a sort of realistic interpretation. So I don't see that it solves many problems.
Let's review the key differences between the Copenhagen interpretation and the transactional interpretation. The Copenhagen interpretation says that the wave function is in fact not a physical object, but instead a representation of our knowledge as observers. It puts a special position on intelligent beings, whereas the transactional interpretation says the wave function is physical and the universe can be non-local, whilst providing insight into the formalism. Within the Copenhagen interpretation, an observer directly affects the wave function and causes it to collapse, whereas within the transactional interpretation, a change in an observer's knowledge is a consequence of the wave function collapse, not the other way round. The Copenhagen interpretation says that non-observables are meaningless, and it gives no leeway for this, whereas the transactional interpretation thrives off of non-observables and provides insight because of them.
Out of the many interpretations of quantum mechanics, which I'm sure you have discussed quite a few in your lectures on this course, which one is the most convincing to you?
So I think I would hold with a sort of emergent notion that at every level of complexity, what's revealed is new physics that's at some level just as fundamental as the level below it. So we fool ourselves if we say the single particle Schrödinger equation is the last word on everything at a microscopic level. First of all, we know that it's generalized in quantum field theory, which solves a whole load of other problems, but there's also good evidence that quantum field theory, at the level of it being right in that it's renormalizable in a technical sense, it's probably only a low energy approximation to some other theory. Okay, so probably at every level you would reveal new physics that is in some sense compatible with every level having its own approximation. Yeah. So I think, I think that's certainly what condensed matter in the 20th century has taught us about how fundamental physics works.
There are several other examples of issues that the transactional interpretation provides insight to, like Renninger's negative result thought experiment and Wheeler's delayed choice experiment. However, these demand a more in-depth explanation of the background physics which exceeds the scope of this video. If you want to read more, we recommend having a look at John G. Cramer's paper, The Transactional Interpretation of Quantum Mechanics. Even though the transactional interpretation seemingly solves many of the Copenhagen interpretation's problems, it is not widely used by physicists today. Why is this? Occam's razor, a general scientific principle, suggests that simpler explanations are better, and it is often quoted by critics of the transactional interpretation. They say it introduces unnecessary complexities into the interpretation, and in reality they are not needed to do quantum mechanics. Often the only part physicists end up using day to day are the first two premises, which are the same for both. Many are unaffected by the actual workings of quantum mechanics. In addition, as I'm sure many of you will consider, the implications of waves travelling backwards in time is not too nice to think about.
In the grand scheme of things, what's your opinion on whether humans have free will?
So I think humans do have free will. I think usually a lack of free will is used as an excuse to do terrible things to people. So I mean, I've always been quite taken by Jean-Paul Sartre's notion that freedom is inevitable. It's not necessarily a positive thing, and that people will do a lot of things to try and escape the inevitability that they have free will, and they use it as an excuse often to absolve themselves of responsibility. And you could think about Samuel Johnson's quote about, someone who acts like a beast takes away the pain of being a human. Mm-hmm. So I think it is inevitable that we have free will at some level, or at least, we think we do.
Yeah, sometimes in classical physics we like to talk a lot about determinism, mm-hmm. and there's been a lot of sort of philosophical argument to try and make compatible the determinism of quantum classical mechanics and ideas of free will. Mm-hmm. But then came this the idea of quantum mechanics, which is a lot more probabilistic and not as deterministic. And would you say that quantum mechanics has anything to contribute to this debate?
No, I don't think so, because I think if you go up to the level of complexity required to discuss human consciousness, you're various layers of complexity away from the quantum mechanics and classical mechanics. So, for example, single particle quantum mechanics has nothing to say about mechanical rigidity, for example. So the thought that it's going to have something to say about consciousness is probably laughable in anything other than a sort of caricature, I think.
How would you feel about the future affecting the past?
I think that that's probably not admissible to modern physics. That we set up quantum field theory, which is the sort of generalization of quantum mechanics that's compatible with special relativity, and really the only ingredient we have is that quantum fields are causal, that for a space-like separation of events your operators must commute. That's a quantum mechanical way of encoding special relativity, and what that implies is at least time ordering. So a philosopher would probably not say that that was a particularly strong way of talking about causality, but I think as physicists that's probably the way that we would do it, and anything that removes that time ordering I think creates more problems than it solves. But it's probably worth noting that conventional single particle quantum mechanics doesn't have that wired into it. Which is probably, the reason why I think people get themselves in lots of tangles about this. So you can just solve a single particle Schrödinger equation, and there's a finite probability for a particle to appear outside its forward light cone, which is forbidden by special relativity. That's a problem solved by quantum field theory, because it just makes a relativistic generalization that prevents that.
Do you have free will? It's definitely a question you might have considered before. The concept is easy to understand. Do you, a human, have complete and total control over every single one of your actions? Maybe, maybe not. It's been a debate since ancient Greece. Classical physics would probably tell you no, the universe's laws are absolute. God does not play dice, as Einstein would say. Atoms act like a tiny game of pool where every movement and bounce of the balls can be calculated, and you being made up of those balls are just as predictable as they are. However, over the past century we've seen a shift, namely in quantum mechanics. The Copenhagen Interpretation places a special role on the intelligent observer, and the universe appears to be indeterministic, and it feels nice, knowing that your choices might actually be your own. It's not just a sequence of events influenced by the ones before, and that may be another reason why we like it so much, why we cling to it, why it makes us feel special in such a big universe. How then does the transactional interpretation make us feel? Yes, it's fully causal. There's no travelling back in time to make sure your father ends up with your mother, but it still feels off, doesn't it? The idea that the location of something in the future could affect the energy transfers of the past. The idea alone that if the quantum world truly does work like this, will it be forever stuck in the minds of humanity that maybe tomorrow affects today? We're not really sure. I don't think it's truly been discussed enough to know how people feel about it. How do you feel about it?